We are going to start a lecture on the ingredients of Bayesian inference. That lecture is very important for the rest of the course, and because the things that we are going to discuss today are going to be reappearing over the course many times. So what are the ingredients of Bayesian inference? We are going to make parallel between the Bayes theorem for events and the Bayes theorem for the distribution functions, the real Bayes theorem. Bayes theorem for events we call Bayes rule, and here we talk about Bayes theorem. So what are the ingredients? We are going to start with the model. Remember, these observations that we got from the experiment are modeled by the statistical model, which is given by distribution, in this case density. We say that xi's are independently distributed as random variables with density f of x given theta. So theta is the parameter, and we got n of these observations. Now, when we think about the sample can be thought as the n-dimensional vector, and x's in this n-dimensional vector are independent, so the joint distribution of x1 up to xn is the product of the individual ones. In this case, the joint distribution would be f of x1 given theta times f of x2 given theta, and so on and so forth, up to f of xn given theta. And you get product I from 1 to n, f of xi given theta. Now, the x's are observations. You can keep them unspecified before the experiment, but once experiment is done and you have x's, you plug x's in this expression. As a function of theta, this expression is called likelihood. So again, you can think about this model, this product, as function of two variables, x's and theta. When x's are observed, you get expression which is called likelihood. Likelihood is a function of theta. According to likelihood principle, which is adopted by Bayesians and even non-Bayesians, all information about the experiment is contained in the likelihood. So the organization of the experiment, the model for the experiment, the observations for the experiment, the parameter information, everything is in the likelihood. Well, name of the parameter and type of parameter. The parameter information is supplemented by the priors, we'll see later. So let's see how one typical likelihood may look like. For example, we sample from exponential distribution. We have three observations. x1 is 2, x2 is 3, and x3 is 1. And since they are from exponential distribution, the likelihood is the product of the densities. But then I plug in x's. If we think about density to be f of x given lambda, to be lambda e to the minus lambda x, what I really do is I'm plugging these x's, 2, 3, and 1, and getting the product with fixed x's. So the result here is the likelihood as a function of parameter, in this case lambda. Sometimes you want to keep data unspecified, and in this case you may have the x's given not explicitly, but you can think of those x's as observed. So let's see what are priors. In this model, fx given theta, theta is the parameter. Now, the frequentist approach to statistics thinks about parameters as fixed unknown number. So in population, you have the model, you have the parameter, and that parameter is something which is fixed unknown. And the inference is concerning that fixed number. The Bayesians put the distribution on the parameter, and that distribution is expressing the degree of uncertainty. So that distribution could be very concentrated, almost point mass at some value if you're very sure about the parameter. But it could be very vague and very broad, and if you're not certain about parameter, that distribution is with big variance. Later in this course, we are going to see how to elicit parameter priors, what kind of priors are there, are they non-informative, and so on and so forth. But for a moment, you just think about prior is a distribution on the space of parameters. So it is pi of theta, usually denoted, and theta is element of the parameter space, capital theta. Now you can think about these x's, which are your measurements that you are modeling in the model, and theta as a vector of two random variables. And the joint distribution of this vector, x and theta, is h of x theta. Now, the marginal distribution of x is distribution of x alone when you account for theta. So simply, you will be taking the joint distribution h of x theta, integrating with respect to theta, and the integral is over parameter space. That is m of x. We saw in some of the last lectures how to find the conditional distributions, from the joint distributions, how to find marginal distribution from joint distribution. In this case, this m of x is called marginal distribution for x, and it is simply marginal distribution from the joint distribution h. Now it's time for Bayes' theorem. Recall the Bayes rule for the events. We had the probability of the intersection, and probability of intersection is the product of probabilities if the events are independent. But if the events are not independent, you have this generalized product rule, and probability of intersection can be represented as probability of A given HI times probability of HI, or equivalently, probability of HI given A times probability of A. They are both the same, equivalent. They are equal to probability of A intersection HI. Now, when you express probability of HI given A, that leads to Bayes' rule from this expression. By analogy, the joint distribution could be represented as the likelihood, or the model, times the prior, or something that we call posterior distribution of theta given x times the marginal. Simply with analogy to the events, probabilities of events, where the probabilities are replaced by densities. Now, if you express the posterior distribution, pi of theta given x, then this expression is Bayes' theorem. Very simple. To get posterior, you get the likelihood, multiply by prior, and divide by marginal. Let's take a look at the example. Suppose that we have observation x, which given theta is normal. Parameter of interest is theta, it is location of normal, and variance is sigma square, assumed known. Now I put the prior on theta, which is again normal with some mean mu and variance sigma square. I may have some information about theta. I may know something about location for theta, and that specifies mu. And I may know something about variability of theta, which would specify tau square. So mu and tau square are elicited. And if they are parameters of the prior, they are called hyperparameters because they are parameters of the distribution on the parameter. Now, when you take the joint distribution h of x, you will be multiplying the likelihood. This is the first part. X here is considered to be fixed, observed, and prior, the second part. Prior is a distribution on theta. Mu is the location. Now you see the product of two exponential distributions, and then you look at just the exponent part, and you look at the exponent, which is difference of two expressions. If you consolidate this difference of these squares so that you have theta minus something squared and x minus something squared, I admit this algebra is not pleasant, but it is very straightforward. It is simply completing the full squares. After some algebra, you get that this expression here is equal to this expression here. This leads actually to product of two normal distributions because we have variable minus something, the quantity squared e, and also variable minus something divided by some variability in the second part. So when we consolidate these to product of two normal distributions, we conclude that theta given x is normal and x, which is marginal, is also normal. Now the mean of this posterior is very important. You see that this mean is compromising what you observed, x, and what you believe, mu. Now the weights of what you observe and what you believe are summing up to 1. And they depend on the variability, which is how sure are you about x and how sure are you about mu. So x is observed and mu is elicited. You get the weight w and weight 1 minus w, combination of x and mu. So you compromise between what you observe and what you believe. Now the posterior mean is this, but because it is normal distribution, the mean, mode, and the median coincide. So in this case, for the posterior, this expression is posterior mean, mode, and median. Now let's see what happens with these weights. If weight W is close to 1, that means that tau square is much bigger than sigma square. And if the weight is closer to 1, then we put emphasis on the observed x. So we estimate the mean of the posterior closer to what we observed in the experiment. But what really that means is the following, that tau square, which is variability of the prior, is much bigger than the variability of observations. So you're quite certain about the observation because sigma square is smaller, and then you put emphasis on what you observe as x. Vice versa, if you have W weight close to 0, then you emphasize what you elicited. But that happens only if the variability of the experiment exceeds the variability of what you believe about the parameter. So in a very natural way, most of these Bayes rules that we are going to discuss are some sort of compromise between what you observe, or the estimator coming only from the data, from the observations, and what you believe, which is estimator coming from the prior.